In this video, we're discussing question 19 on practice exam 3.1 in the fall 2021 semester in Chem 1211. And this question asks about the molecular shape or molecular geometry, how we've predominantly called it, of a hypothetical molecule XF4. So the problem is all about molecular geometry, and we've got a molecular formula. It's just a little bit ambiguous or broad with XF4 as the formula, but we do have information about the X atom. Specifically, we know that the X atom is a nonmetal with 8 valence electrons. And it doesn't say nonmetal, but it should. 8 valence electrons. The reason nonmetal should be there is this allows us to conclude that this is a group 18 element. And this should allow you to conclude that this is a group 18 element. If it's not explicitly stated that the element is a metal, go ahead and assume it's a nonmetal. So 8 valence electrons in XF4. Now, where does that put us on the periodic table? Group 18 and an element like xenon, a noble gas. The noble gases tend not to form compounds. Xenon is one of the few that has been observed to actually form compounds, and XEF4, believe it or not, is actually a known compound. So let's start by drawing a Lewis structure for XEF4, because after all, we're going to have to get all the way to the molecular geometry from the Lewis structure, and we can step through this process systematically in this problem. XEF4, what's the total number of valence electrons in this? We already identified 8 for the xenon. We've got 7 on each of the fluorines. So that's 4 times 7, 28 plus 8 is 36 valence electrons total in this molecule. This would apply regardless of the identity of X for any element with 8 valence electrons. So to draw the Lewis structure, we're going to need to make sure to account for all 36 of those electrons. And let's start by putting xenon at the center and the 4 fluorines more electronegative right around the periphery. And let's go ahead and lay down lone pairs on the fluorines to satisfy the octet rule at those atoms. When we do this, we're left with 2 pairs of electrons unaccounted for, and the xenon is already satisfying the octet rule, but so are the fluorines. And so the only place we really have left to put down those pairs of electrons are at the xenon atom, something like this. Now, to get geometric information from this Lewis structure, the next step is to determine what I call the steric number, or the number of electron domains, number of charged clouds, number of distinct electron blobs, if you will, around the xenon atom. This is concisely called the steric number. And to count that, we look at each double, triple, and single bond as a single domain, as one domain. And here we've got 4 single bonds to the xenon atom, so that's 4 domains. We've got 2 lone pairs. So the steric number here is 6. And there is an electron geometry that corresponds to the steric number of 6. That electron geometry is octahedral. Octahedral. This is the electron geometry. This is the geometry of the electron domains about the central atom. To get the molecular geometry, we now need to consider the lone pairs. So what I'm going to do is actually highlight the lone pairs in a different color. Let's highlight the lone pairs in red and look only at the positions of the fluorines and xenons, only the atomic positions, and ask what shape or geometry do I see right there? Well, actually the Fs and the xenon are all in a common plane, and that plane has the shape of a square because all 4 XEF bonds are equivalent. So the geometry we're looking at here is square planar. And this is what we have called the molecular geometry. Molecular geometry. Because it refers only to the positions of the atoms about the central atom. Square planar molecular geometry, and there it is as the last option from these choices, square planar.